There's a reason Jupiter has 67 moons, and we're about to get number 68, whether we like it or not. 3I/Atlas, the interstellar object astronomers have been tracking since 2024, isn't wandering aimlessly through our solar system. New orbital calculations reveal something that's making scientists deeply uncomfortable. This thing is executing a precision approach to Jupiter's Hill radius, hitting a gravitational sweet spot with accuracy that shouldn't exist in nature. We're not talking about a close flyby. We're talking about spacecraft-level targeting of the perfect parking zone for long-term surveillance. Stay with me until the end, because what we're watching may be the deployment phase of something that's been planned for longer than human civilization has existed. You'll want to stay close as 3I/Atlas continues its journey through our solar system and the data keeps rolling in. Subscribe and follow along, because every new observation brings us closer to understanding what we're actually looking at here. Now let's dim the lights and dive into this cosmic mystery together. You know what keeps astronomers up at night? It's not asteroids. It's not black holes. It's not even the fact that 95% of the universe is invisible to us. What really haunts them is precision, where there shouldn't be any. When something from the cosmic void arrives at our doorstep, moving with the exactness of a launched satellite, that's when things get interesting. That's when things get uncomfortable. And that's exactly what's happening with 3I/Atlas, an object we've been calling a comet, but which might be something else entirely. Something deliberate. Let me walk you through what has everyone so rattled. 3I/Atlas entered our solar system in 2024, and at first glance, it looked like your standard issue interstellar visitor. A little ice, a little rock, probably tumbling through space for millions of years before wandering into our neighborhood by accident. Astronomers logged it, tracked it, and prepared to watch it swing around the sun and disappear back into the darkness. Business as usual. Except then, someone actually ran the numbers on where this thing was going. Not just where it came from, but where it's headed. And that's when the math stopped making sense. 3I/Atlas is not on a random inbound path. It's not drifting aimlessly through the solar system like some cosmic tumbleweed. The trajectory calculations show something far more unsettling. This object is moving toward a very specific destination, a gravitational sweet spot around Jupiter called the Hill radius, and it's hitting that target with a precision that shouldn't exist in nature. We're talking about spacecraft-level accuracy here, the kind of exactness you only see when something is being guided or controlled. So what exactly is the Hill radius? Think of it as Jupiter's personal gravity bubble, the region of space where Jupiter's gravitational influence dominates over the sun's. Inside this boundary, objects feel Jupiter's pull more strongly than the sun's, which makes it the perfect parking zone for satellites. Natural moons form here. Human-made probes aim for this zone when they want to orbit Jupiter efficiently. It's the gravitational equivalent of a harbor, a stable place where something can stay without burning through fuel or fighting against competing forces. Jupiter's Hill radius extends roughly 53 million kilometers from the planet's center. It's enormous, a cosmic territory roughly the size of Mercury's entire orbit around the Sun. Now, here's where things get weird. The calculated intercept point for 3I/Atlas, 53.445 million kilometers, plus or minus 0.06 million kilometers. That's not close. That's pinpoint accurate. That's threading a needle on a galactic scale. To put this in perspective, imagine throwing a dart from New York and hitting the bullseye of a dartboard in Los Angeles, except the dartboard is moving, and you're also moving, and there's no air, and you threw the dart 7 years ago. That's the level of precision we're talking about. Natural comets don't do this. They can't. Let me be clear about what we mean by targeting versus close approach. Plenty of objects pass near planets. That's normal. Space is full of rocks and ice balls wandering around on chaotic paths. Sometimes they get close to Jupiter or Saturn purely by coincidence. But there's a massive difference between passing near something and hitting a specific gravitational boundary within a margin of error measured in thousands of kilometers. The latter requires either impossible luck or active guidance. And 3, I/Atlas isn't just getting close to Jupiter's Hill radius. It's hitting the boundary with surgical precision, the kind of accuracy that mission planners at NASA spend years calculating for actual spacecraft. The official designation from NASA still classifies 3 I/Atlas as a comet. That's the bureaucratic label in the database. But a growing number of independent astronomers, including Avi Loeb's team at Harvard, are now arguing publicly that the observational data doesn't fit a natural comet at all. Instead, they say the trajectory matches what you'd expect from an insertion maneuver, a controlled approach designed to place an object into a specific orbital zone. This isn't fringe stuff anymore. These are credible scientists with access to the same data NASA has, and they're looking at the numbers and reaching a very different conclusion. Here's what makes the situation even stranger. 3 I/Atlas approached perihelion, its closest point to the Sun, back in early 2025. Comets typically behave erratically after perihelion because the solar heat causes volatile ices to sublimate violently, creating jets of gas that push the comet around, unpredictably. You'd expect the trajectory to loosen up, to become messier and harder to predict. Instead, the opposite happened. The approach vector tightened. The path toward Jupiter's Hill radius became more refined, more exact, as if someone had made a course correction after the Sun encounter. That's not how sublimating ice behaves. That's how thrusters behave. And then, there's the Earth problem. 3 I/Atlas passed relatively close to Earth on its way to Jupiter. Close enough that if this were an alien probe interested in humanity, you'd expect some kind of response. A change in orientation, maybe. A shift in velocity. Some kind of thermal signature indicating observation equipment activating. But nothing happened. No braking. No orientation change. No thermal anomalies. The object completely ignored us. It flew past Earth like we weren't even there, like a car on the highway passing an exit without slowing down. That indifference is more disturbing than hostility would be, because it suggests we're not the destination. We're just scenery on the way to somewhere more important. But here's the detail that really gets under your skin. During the period when 3 I/Atlas was hidden behind the Sun from Earth's perspective, something happened. The object accelerated slightly. Not a lot, just enough to be measurable, but enough to adjust the trajectory in precisely the way needed to refine the approach to Jupiter's Hill radius. This acceleration occurred during solar conjunction, a window of time when solar glare prevents telescopes from tracking objects accurately. Convenient timing, if you think about it. Almost like someone knew when they wouldn't be watched closely. If 3 I/Atlas is a vehicle, if it's a carrier craft of some kind, then its flyby of Earth makes perfect sense. We were never the target. We were never part of the mission plan. The real event, the actual objective, happens at Jupiter. And that possibility, that we might be witnessing the arrival of something intentional, something with a specific goal that has nothing to do with us, changes everything we thought we understood about our place in the solar system. Because if something out there is building infrastructure around Jupiter, we need to know what that infrastructure is for. And more importantly, we need to understand why they're building it right next door. There's a specific kind of paranoia that astronomers rarely talk about publicly, but it's there, lurking beneath the surface of every conversation about interstellar objects. It's the fear of the blind spot, the terror that something could happen in the one place we can't see, during the one window when our instruments go dark, and we'd never know until it was too late. For 3 I/Atlas, that blind spot was solar conjunction, and what happened during those hours has become the most hotly debated mystery in modern astronomy. Solar conjunction is a predictable event. It happens when Earth, the Sun, and a target object align, placing the Sun directly between us and whatever we're trying to observe. During this period, solar glare overwhelms our telescopes. Radio signals get swamped by the Sun's electromagnetic noise. Optical observations become impossible. We go blind for anywhere from a few days to several weeks, depending on how close the alignment is. For 3I/Atlas, the blackout window lasted between 40 and 60 hours. A relatively short conjunction, but long enough that precise tracking became impossible. When the object emerged from behind the Sun's glare, astronomers immediately noticed something had changed. The change was subtle, but unmistakable. 3I/Atlas had experienced what scientists call a non-gravitational acceleration event. In plain English, something had pushed the object in a way that gravity alone couldn't explain. The velocity had increased slightly, and more importantly, the direction had shifted in precisely the manner needed to refine the approach to Jupiter's Hill radius. This is where the scientific community splits into two camps, each offering radically different explanations for what they're seeing in the data. The conventional explanation goes like this. Comets are dirty snowballs, mixtures of ice and rock left over from the solar system's formation. When they get close to the Sun, the ice heats up and sublimates, turning directly from solid to gas without passing through a liquid phase. This outgassing creates jets of vapor that can push the comet around, producing measurable accelerations that aren't caused by gravity. It's a well-documented phenomenon. We've seen it happen with dozens of comets over the years. So when 3I/Atlas showed a non-gravitational acceleration after perihelion, the natural assumption was that solar heating had triggered outgassing, and the resulting jets had nudged the object onto a slightly different path. Case closed, mystery solved, nothing to see here. But here's where the conventional explanation starts to break down under scrutiny. Cometary outgassing is chaotic by nature. When ice sublimates on an irregularly shaped, rotating body, it creates jets pointing in random directions. These jets appear and disappear as different parts of the comet rotate into and out of sunlight. The result is usually a tumbling, erratic motion that's extremely difficult to predict. Comets don't fly straight after perihelion. They wobble. They spin. They change direction in ways that require constant recalculation. Yet 3I/Atlas displays an unusually symmetrical coma, the cloud of gas and dust surrounding the nucleus. There are no detectable jets, no rotating outgassing sources, none of the typical signs of asymmetric sublimation. The object looks remarkably stable, almost artificially so. More troubling is the direction of the acceleration. When you map the velocity change vector, when you calculate exactly which way the push occurred, it points in. The precise direction needed to tighten the approach to Jupiter's Hill radius. Not approximately, not close enough, exactly. It's as if someone calculated the optimal correction burn and executed it with textbook precision. Natural outgassing doesn't work that way. Gas jets from sublimating ice don't care about orbital mechanics. They push randomly, and the resulting trajectory changes are messy and unpredictable. This was clean. This was targeted. Some astronomers have pointed out that certain comets do exhibit asymmetric heating patterns that can create surprisingly consistent thrust over short periods. If the ice distribution inside the nucleus is non-uniform, if there's a concentration of volatiles on one side of the object, then heating from the Sun could theoretically produce a more directional acceleration. It's possible, though unlikely, that 3I/Atlas just happened to have exactly the right internal structure to create exactly the right push in exactly the right direction at exactly the right time. Possible, but when you string together that many coincidences, you start to wonder if you're looking at bad luck or deliberate design, Then there's the timing issue. The acceleration occurred during the telemetry blackout, the 40 to 60-hour window when precise tracking wasn't possible. Not before conjunction, when we could have watched it happen in real time. Not after the object was fully clear of solar glare, when we could have measured every detail. Right in the middle of the blind spot, when verification was impossible. Skeptics will correctly point out that this timing makes perfect sense for a natural explanation too. Perihelion is when comets are most active, and perihelion coincides with conjunction, because that's just how orbital geometry works. The sun is in the way, because the comet is closest to the sun. It's not suspicious. It's just physics. But if you were designing a probe that needed to make a course correction, if you wanted to adjust your trajectory without drawing attention, you'd do it here too. You'd wait for perihelion because the solar energy is strongest, giving you maximum power for any onboard systems. You'd wait for conjunction because Earth's telescopes can't track you precisely. And if your propulsion system happened to produce exhaust that looked a lot like sublimating ice, well, that's just good camouflage. Solar heating provides both energy and cover. It's the perfect moment for a burn, natural or otherwise. After conjunction, after the acceleration, 3I/Atlas entered what some researchers are calling the corridor. This is a specific volume of space, a narrow pathway defined by gravitational forces and orbital mechanics that leads directly to the Hill radius intercept. Once you're in the corridor, once you're on this particular trajectory with this particular velocity, you're locked in. The path is set, and 3I/Atlas is deep in the corridor now, moving inexorably toward its rendezvous with Jupiter's gravitational boundary. The question that nobody can answer definitively is whether the object entered the corridor by chance or by choice. Did random outgassing happen to push it onto the one trajectory out of billions that leads precisely to the Hill radius? Or did something make a deliberate adjustment during the one window when we couldn't watch closely? The data can support both interpretations, which is why this debate has become so contentious. Scientists are looking at the same numbers and reaching opposite conclusions because the margin between natural and artificial behavior is razor thin. If this was a course correction, if 3I/Atlas used perihelion as a cover for a controlled burn, then we're dealing with something that understands orbital mechanics at an advanced level. Something that knows how to use solar radiation for power or propulsion. Something that planned this maneuver long before entering our solar system, calculating the exact moment and magnitude of thrust needed to hit the target. And something that may have deliberately chosen a method of propulsion that mimics natural processes, making it almost impossible for observers to distinguish between accident and intent. That level of sophistication is frankly terrifying, because it suggests we're not just being visited. We're being strategically approached by something that doesn't want to be identified until it's ready. Humanity has spent the better part of a century imagining first contact. We've written thousands of books, made hundreds of films, and developed countless protocols for how we'd respond if something intelligent arrived from the stars. Most of these scenarios involve some form of interaction: hostile invasion, peaceful greeting, scientific exchange, cultural misunderstanding, whatever the specifics. We always assume they'd notice us. We assume we'd matter. 3I/Atlas is forcing us to confront a far more unsettling possibility. What if we don't matter? What if something arrived from another star system, passed right by Earth, and didn't even slow down to look? The psychological impact of this indifference is difficult to overstate. We're conditioned to think of ourselves as important, as the center of the story. When we look at the cosmos, we imagine civilizations out there wondering about us the same way we wonder about them. We picture alien telescopes pointed at Earth, scientists on distant worlds debating whether our radio signals indicate intelligence or just natural phenomena. We envision scenarios where contact happens because they seek us out, or we seek them out. But either way, there's mutual interest. 3 I/Atlas challenges that entire framework. If it's artificial, if it's a probe or vessel of some kind, then its complete disinterest in Earth tells us something profound and deeply uncomfortable about our cosmic significance. Let me walk through what didn't happen during the Earth flyby, because sometimes absence is more revealing than presence. 3 I/Atlas passed within a range where any probe equipped with even basic sensors could have gathered enormous amounts of data about our planet. Atmospheric composition, electromagnetic emissions, thermal signatures, all the hallmarks of a technological civilization broadcasting its presence across multiple spectrums. This was an opportunity for reconnaissance, for observation, for at least a cursory scan of what's happening on this blue marble in the habitable zone. And 3 I/Atlas did absolutely nothing. No maneuver adjustments, no orientation changes that might indicate cameras or sensors swiveling toward Earth. No thermal variations suggesting equipment activating. No unusual radio reflections. No albedo changes. Nothing. From an engineering standpoint, ignoring Earth makes sense only if Earth wasn't part of the mission parameters. If you're driving from New York to Los Angeles, you don't stop in every small town along the way unless you have a specific reason to. You might glance out the window as you pass through, but you don't exit the highway for a closer look unless something catches your interest. 3 I/Atlas drove right past us without taking the exit, which tells us that whatever its destination and purpose might be, we're not it. We're just one more G-type star with some rocky planets. Nothing worth the fuel expenditure for a detour. But here's where it gets interesting from a strategic perspective. If you're an advanced civilization sending probes to other star systems, Jupiter is exactly where you'd want to set up shop. Not Earth, not Mars. Jupiter. And there are very good reasons for this choice that have nothing to do with biology or habitability and everything to do with energy and positioning. Jupiter's magnetosphere is the largest and most powerful in the solar system, a massive region of charged particles and magnetic fields that dwarfs anything Earth can produce. For any civilization that knows how to tap electromagnetic energy, Jupiter is a cosmic power plant. Free energy on a scale that makes even Dyson sphere concepts look quaint. You could run entire fleets of autonomous probes indefinitely just by harvesting what Jupiter's magnetosphere generates naturally. Then there's orbital stability. The Hill radius isn't just a gravitational boundary. It's a parking zone where objects can remain in relatively stable orbits without constant course corrections. You could place a satellite or probe in this region, and it would stay there for centuries with minimal station-keeping requirements. No fuel burned, no complex maneuvers, just letting Jupiter's gravity do the work of keeping your hardware in position. For a long-term observation mission, for anything designed to monitor a star system over extended timescales, this is ideal real estate. And the view from Jupiter is spectacular, at least from a surveillance perspective. You're far enough out that you can see the entire inner solar system spread out before you. Earth, Mars, Venus, Mercury, all visible, all trackable. Radio emissions from Earth would wash over your position constantly. You'd have a front row seat to everything happening in the warm inner orbits where rocky planets and complex chemistry create the conditions for life. Meanwhile, you're sitting in a radiation-soaked magnetic hellscape where nothing biological could survive, which means any organic civilization like ours isn't going to come poking around your equipment anytime soon. It's the perfect observation post, close enough to see everything, but far enough to remain undisturbed. This strategic reasoning points to a conclusion that many people find more frightening than outright hostility. 3 I/Atlas might not be here for us at all. We might be incidental. Background noise in a mission focused on long-term infrastructure deployment. Think about it from their perspective, whoever they are. You send a probe to a star system not to make contact with whatever primitive civilizations might be stumbling around on rocky planets, but to establish a permanent monitoring presence. You want data. You want a communications relay. You want a base of operations that can function autonomously for thousands of years, collecting information and transmitting it back home. Earth is just one of many objects in the system worth monitoring, no more special than the asteroid belt or Saturn's moons. The human fear fantasy has always been invasion. We imagine fleets of ships arriving to strip mine our resources or enslave our population or wipe us out as competitors. These scenarios assume we're important enough to threaten, valuable enough to exploit. The dark reality suggested by 3I/Atlas is far more existentially troubling. We might not be strategically important at all. Our planet, our civilization, our entire existence might be nothing more than data points in a survey mission, interesting enough to log, but not worth interacting with directly. We're the locals, and they're not here to conquer us, or trade with us, or even talk to us. They're here to set up infrastructure that serves purposes we can't even guess at. NASA and ESA maintain that 3I/Atlas is a natural interstellar comet with no maneuverable capability. They point to the lack of radio emissions, the absence of any clear artificial signatures, the consistency of its behavior with known cometary physics. These are all valid points. But when you step back and look at the pattern, the precision of the trajectory, combined with the complete disinterest in Earth, it paints a picture that's hard to dismiss. This doesn't look like random chance. This looks like planning. This looks like execution of a mission we're not privy to. Historians might find parallels in Earth's own colonial past, though the comparison is imperfect. When European powers explored the Americas, they often established forts and trading posts in strategic locations, places with good harbors or access to rivers or defensive advantages. The indigenous populations nearby were sometimes engaged with, sometimes ignored, depending on whether they were seen as useful or threatening or irrelevant. 3I/Atlas might represent that same calculated assessment applied on an interstellar scale. Jupiter is strategically valuable. Earth is not yet relevant enough to engage with directly, and that realization that we might be the indigenous population watching ships sail past to a more important port is a humbling and terrifying prospect. Because it means contact, if it ever comes, will happen on their terms and their timeline, when and if they decide we're worth the effort of saying hello. There's a concept in astrobiology that doesn't get discussed much in public forums, probably because it sounds too much like science fiction, even though it's based on perfectly reasonable physics. The idea is that advanced civilizations don't send themselves to other star systems. They send machines. Small, durable, autonomous probes that can survive the journey, arrive at the destination, and then do something we rarely consider in our contact fantasies. They multiply. They disperse. They build networks. This is the core of Sentinel theory, and 3I/Atlas might be giving us a front row seat to exactly how such a deployment operation works. Let me explain what Sentinel theory actually proposes, because the details matter. The theory suggests that interstellar exploration isn't conducted by massive crewed vessels or even single large probes. Instead, a carrier craft arrives at the target star system carrying dozens or even hundreds of smaller autonomous units. These units are designed for long-term monitoring and data collection. The carrier approaches a gravitationally stable region, something like Jupiter's Hill radius, and then performs a dispersion event. The smaller probes detach, break into different orbits using minimal propulsion, and position themselves at strategic points throughout the system. Some might head for Lagrange points. Others might settle into orbits around major planets or moons. A few might even venture into the inner system to observe rocky planets more closely. The beauty of this approach from an engineering standpoint is efficiency. You don't waste energy and resources sending individual probes to every star system. You send one carrier that can deploy a complete observation network upon arrival. Once the deployment is complete, the carrier either stays in system as a communications hub or continues on to the next target, leaving the network to operate autonomously. Over time, over thousands or millions of years, this strategy could fill the galaxy with sentinel networks, each one quietly monitoring its assigned star system and transmitting data back to whoever built them. If any of these systems develop technological civilizations, the sentinels are already in place to observe, record, and report. Jupiter's Hill radius is nearly perfect for this kind of operation, and understanding why requires a bit of orbital mechanics. The Hill radius defines the region where Jupiter's gravity dominates, but within that region are even more refined zones of stability called Lagrange points. These are specific locations where the gravitational forces of Jupiter and the Sun balance in ways that allow objects to maintain fixed positions relative to both bodies. The L1 and L2 points are particularly interesting because they sit along the line connecting Jupiter and the Sun, creating natural parking spots where a probe could hover indefinitely with minimal energy expenditure. L1 sits between Jupiter and the Sun, about 50 million kilometers from Jupiter's center. An object at L1 can observe both the inner solar system and Jupiter itself without ever leaving that position. It's a surveillance platform that requires almost no fuel to maintain. L2 sits on the far side of Jupiter, roughly the same distance out, but in the opposite direction. An object at L2 is perpetually in Jupiter's shadow from the Sun's perspective, making it nearly invisible to Earth-based telescopes. It's the perfect hiding spot, a dark zone where you could park an entire fleet of probes, and nobody would notice unless they went looking specifically. The Hill radius and Lagrange points together create a three-dimensional lattice of stable positions where autonomous probes could position themselves for centuries or longer. No complex station-keeping maneuvers, no fuel burned fighting against gravitational perturbations, just pure celestial mechanics doing the work of maintaining position. For a civilization thinking on timescales of thousands of years, this is how you build lasting infrastructure in a foreign star system. You use the gravity wells and orbital resonances that are already there, turning the system's own physics into your anchor points. Jupiter itself offers additional advantages that make it ideal for long-term autonomous operations. The magnetosphere is enormous, extending millions of kilometers in all directions, and carrying enough energy to power entire cities. Any probe equipped with electromagnetic harvesting technology could draw continuous power from the charged particle flux, eliminating the need for nuclear reactors or solar panels. You could run sophisticated sensor arrays, communication systems, and computation hardware indefinitely without worrying about batteries dying or fuel running out. The radiation environment, while lethal to biological organisms, is actually protective for certain types of electronics. High-energy particles can damage semiconductors. Yes, but they also create a natural barrier against detection. Radio signals get scattered and absorbed by the plasma in the magnetosphere. Optical observations are difficult because the background glow from auroras and particle interactions creates noise. If you wanted to hide electronic signatures from primitive civilizations in the inner system, Jupiter's radiation belts are nature's perfect jamming system. So what would deployment actually look like from an observational standpoint? This is where things get speculative, but grounded in physics we understand. Imagine 3 I/Atlas approaching the Hill radius boundary over the next few months. As it crosses into Jupiter's gravitational domain, instruments on Earth might detect what appears to be a fragmentation event. Not an explosion, nothing violent, just the parent object coming apart into multiple smaller pieces. This happens with natural comets all the time, so initially, nobody would think twice about it. Ice and rock separating due to tidal forces or thermal stress, perfectly normal. But then the fragments don't behave like comet debris. Instead of dispersing chaotically, they break. They slow down in coordinated ways. They begin moving toward different destinations, some heading for L1, others toward L2, a few perhaps diving deeper into the Jovian system toward Io or Europa. The individual objects are small, maybe a few meters across, with low albedo surfaces that make them nearly impossible to track optically. Within weeks, they've scattered across the Hill radius region, each one settling into a stable position where it can monitor the inner solar system indefinitely. From Earth, we'd see a comet that fragmented near Jupiter. Nothing unusual about that. What we wouldn't see is the network being established right under our noses. Dozens of autonomous probes taking up residence in the solar system's gravitational furniture. They'd be too small to resolve individually, too faint to detect unless you knew exactly where to look, and operating in a radiation environment that makes electronic reconnaissance nearly impossible. By the time anyone realized something strange had happened, the deployment would be complete and the network operational. Some researchers have pushed this theory even further into speculative territory. They argue that 3I/Atlas might not be the first carrier to arrive. Oumuamua, the first confirmed interstellar object detected in 2017, exhibited bizarre acceleration patterns that some interpreted as a light sail or outgassing from an unusual composition. But what if Oumuamua was a scout, a preliminary probe sent to assess the solar system before the main mission arrived? What if 3I/Atlas is actually a resupply vessel or a node delivery craft for a network that's already been here for years, hidden in plain sight among Jupiter's dozens of known irregular moons? This is unverified. Let me be clear. There's no direct evidence that previous interstellar objects were artificial or that any kind of probe network currently exists around Jupiter. But the pattern fits theoretical models proposed by scientists studying how advanced civilizations might explore the galaxy. You don't visit each system once and leave. You establish permanent presence. You create infrastructure that can observe and report over geological timescales. And you do it quietly, using the natural environment to hide your activities from whatever primitive civilizations might be emerging on rocky planets in the habitable zone. If Sentinel theory is correct, if 3I/Atlas is here to deploy a monitoring network, then we're witnessing something unprecedented in human history. We're watching, in real time, as our solar system gets claimed by an intelligence that didn't bother to ask permission or announce its intentions. They're moving in next door, setting up permanent surveillance, and we have no way to stop it, and no clear method even to confirm it's happening. The probes would be small, silent, and strategically positioned in places we rarely look. By the time we develop the technology to search for them properly, they'll have been watching us for decades, collecting every radio transmission, tracking every satellite launch, recording every step of our stumbling progress toward becoming a spacefaring civilization ourselves. And the truly terrifying part? We might never know they're there until they decide it's time to let us know. Scientific consensus is a fragile thing, especially when it comes to objects that don't behave the way textbooks say they should. 3I/Atlas has become a lightning rod for debate within the astronomy community, splitting researchers into camps that view the same data through entirely different interpretive frameworks. The public sees a unified scientific front, press releases from NASA and ESA describing a fascinating interstellar comet. Behind the scenes, in academic journals and conference presentations and private correspondence, there's a war being fought over what this object actually is and what its trajectory really means. The central question is deceptively simple. Can natural outgassing explain the observed trajectory, or does the precision of the approach to Jupiter's Hill radius require active guidance? This isn't a philosophical debate. It's a mathematical one, and math doesn't care about what we want to believe. The problem is that small uncertainties in the initial observations get magnified enormously when you try to project a trajectory backward across interstellar distances or forward to a specific target. An error of 0.001 degrees in the angle becomes millions of kilometers of uncertainty by the time you reach Jupiter. So when skeptics argue about the Hill radius intercept, they're not denying the numbers. They're questioning whether the numbers are precise enough to distinguish between coincidence and intent. Let me break down the arguments against the natural explanation, because they're more sophisticated than simple conspiracy thinking. First, there's the issue of trajectory refinement. Cometary jets produce thrust. That's well-established physics, but the thrust is directionally random unless you have a very specific internal structure that creates asymmetric outgassing. The ice has to be concentrated on one side of the nucleus. The rotation has to be aligned so that the sublimating surface faces the right direction. And the timing of the outgassing has to coincide perfectly with the moment when a course correction is needed. String all those requirements together, and you're asking for a very specific set of coincidences. Possible? Yes. Likely? That's where opinions diverge. Second, there's the coma symmetry problem. Most active comets display irregular, patchy comas with visible jets streaming from specific regions on the nucleus. The jets appear and disappear as the comet rotates, creating a time-variable appearance that astronomers can map to understand the object's shape and spin. 3. I/Atlas doesn't show this behavior. Its coma is unusually uniform, almost eerily smooth, as if the outgassing is happening evenly across the entire surface, or not happening at all. Some researchers argue this could result from a very slow rotation period, or a nearly spherical shape, both of which are rare, but possible. Others point out that a smooth coma is exactly what you'd expect from an artificial object with no outgassing at all, just reflected sunlight and maybe some surface ablation from micrometeoroids. Third, there's the fragmentation rate issue. Natural comets falling apart near the sun typically show dramatic breakup events, with large fragments separating and distinct debris trails forming over days or weeks. 3. I/Atlas has been remarkably intact throughout its journey. Minor debris has been detected, yes, but nothing like the catastrophic fragmentation you'd expect from a loosely bound pile of ice and rock undergoing extreme thermal stress. It's holding together better than most comets do, which is strange for an object supposedly undergoing violent outgassing, strong enough to change its trajectory. Now, let's look at the arguments in favor of the natural explanation, because they're equally valid and grounded in real physics. Comets are weird. We've studied dozens of them up close, and every single one surprises us with unexpected behavior. Some have multiple active regions that turn on and off seemingly at random. Others show delayed outbursts days or weeks after perihelion as heat penetrates into the interior. A few have exhibited sustained thrust in specific directions due to nothing more exotic than asymmetric ice distribution and solar heating. Comet 67P Churyumov-Gerasimenko, which the Rosetta spacecraft studied extensively, showed complex outgassing patterns that looked almost artificial in their regularity, but were ultimately traced to the comet's weird, duck-shaped structure and how different regions heated up as it rotated. The math of orbital fitting is genuinely tricky when you have limited observations spread across months, when you're trying to account for gravitational perturbations from multiple planets, when you're dealing with non-gravitational forces that might or might not be present. The resulting trajectory calculations have error bars. Those error bars can hide a lot of uncertainty. Maybe the Hill radius intercept isn't as precise as it appears. Maybe we're seeing an artifact of how the data was processed, which orbital models were used, which observations were weighted most heavily in the fit. Garbage in, garbage out applies even in astronomy. Bad data produces bad conclusions, and we won't know if the data was actually good enough until we see what happens when 3 I/Atlas actually reaches Jupiter. There are also internal technical debates that rarely get discussed outside specialist circles. For example, Different models of ice behavior produce different predictions for how comets should move. Crystalline ice sublimates differently than amorphous ice. Water ice behaves differently from carbon dioxide ice or methane ice. If 3I/Atlas has an unusual composition, something we haven't seen before, because it formed in a different stellar system with a different chemistry, then all our models for how it should behave might be wrong. We could be looking at perfectly natural physics that just doesn't match what we're used to seeing in solar system comets. Then there are the whispers, the fringe claims that circulate in online forums and occasionally leak into more respectable venues. Some people insist that early tracking data was smoothed or filtered to remove anomalies, that certain observations didn't fit the comet narrative and were quietly excluded from the official orbital solutions. Others claim that the Hill radius match was noticed much earlier than publicly acknowledged, but kept quiet to avoid triggering public panic or conspiracy theories. A few voices suggest that JPL quietly revised its orbital calculations after community pushback, tweaking the numbers to make the trajectory look more natural. These claims are unverified and mostly unprovable. Institutional astronomy operates with enough transparency that large-scale data manipulation would be difficult to hide. But the fact that these whispers exist tells you how divisive this object has become. What's not in dispute is the observational mystery at the core of this whole debate. 3I/Atlas has a persistent forward-facing halo, a slight brightening in the direction of travel that doesn't match typical comet dust distribution. It's fragmenting more slowly than thermal models predict. No major jets have been detected in any spectroscopic observations, which is weird for something supposedly active enough to change its own orbit. The data is real. The measurements are solid. The mystery is in figuring out what story the data is telling us. Are we looking at a natural comet with an unusual composition and structure that happens to be approaching Jupiter with improbable precision? Or are we looking at something artificial that's mimicking natural processes well enough to maintain plausible deniability? The scientific method demands that we default to natural explanations until evidence conclusively rules them out. But as the trajectory gets refined with each new observation, as the approach to the Hill radius gets confirmed again and again, the uncomfortable questions get harder to dismiss. Because at some point, coincidence stops being a satisfying explanation, and you have to consider alternatives that challenge everything we thought we knew about our place in the galaxy. 3I/Atlas doesn't exist in isolation. It's the third confirmed interstellar object we've detected passing through our solar system, and when you line up all three and examine their properties side by side, a pattern starts to emerge. Or maybe it doesn't. Maybe we're just pattern-seeking primates staring at random noise and inventing narratives. But the data points are there, undeniable, and they're weird enough that even conservative astronomers are starting to ask uncomfortable questions about what's really flying past our cosmic doorstep. Let's start with Oumuamua, because that's where this whole interstellar object obsession began. Detected in October of 2017, Oumuamua was like nothing we'd ever seen before. Its trajectory confirmed it came from outside the solar system, which was exciting enough on its own. But then the observations started rolling in, and nothing made sense. The object was elongated, maybe 10 times longer than it was wide, with a highly reflective surface. It tumbled through space in a complex rotation pattern, and most bizarrely, it accelerated away from the sun in a way that couldn't be explained by gravity alone. Something was pushing it, but there was no visible coma, no tail, no signs of the outgassing that should accompany cometary acceleration. Avi Loeb proposed that Oumuamua might be a light sail, a thin artificial structure pushed by solar radiation pressure. This idea was met with enormous skepticism, and rightly so. Extraordinary claims require extraordinary evidence, and the evidence for artificial origin was circumstantial at best. But the natural explanations had problems too. If Oumuamua was a comet, why no coma? If it was just a weird rock, what caused the acceleration? Hypotheses involving hydrogen icebergs or nitrogen ice from Pluto-like worlds got proposed and debated, each with its own set of assumptions and difficulties. 5 years later, we still don't have consensus on what Oumuamua actually was. Then came 2I/Borisov in 2019, and this one looked reassuringly normal. It had a proper coma. It showed outgassing consistent with water ice and carbon monoxide. Spectroscopic analysis revealed a composition similar to solar system comets. 2I/Borisov let everyone relax a little. Proof that most interstellar objects are probably just interstellar comets. Nothing exotic, nothing artificial. Just chunks of ice. And rock ejected from other stellar systems during planet formation, wandering the galaxy until they happen to pass through ours. Crisis averted, normal science restored. And now we have 3I/Atlas, which somehow manages to be more unsettling than Oumuamua despite looking more like a conventional comet. It has a coma. It shows signs of activity, but the trajectory is too precise, the acceleration too well timed, the target too specific. It's like someone learned from Oumuamua's mistakes, figured out that obvious anomalies attract too much attention, and designed the next probe to be just comet-like enough to avoid immediate detection while still accomplishing its mission objectives. That's paranoid thinking, I'll admit. But when you're dealing with objects that might be the first evidence of extraterrestrial technology, a little paranoia feels justified. The scientific frameworks for understanding these objects are evolving rapidly. Light sail hypotheses aren't just about Oumuamua anymore. Researchers are exploring how thin film materials, possibly just micrometers thick, could be pushed by solar radiation across interstellar distances. You don't need engines or fuel, just a large surface area and patience. Launch 1,000 light sails toward nearby star systems and wait 1,000,000 years. Some will arrive, some will collide with debris, some will get pulled into stars, but a few will make it through, and those few can deploy their payloads and start observing. Hollow body hypotheses suggest that interstellar probes might be designed as shells rather than solid objects, maximizing surface area while minimizing mass. This makes them easier to accelerate and harder to detect because they don't reflect light the way solid bodies do. Some researchers are even exploring fractal geometries, structures that repeat at multiple scales to create enormous effective surface areas within compact volumes. These are all speculative ideas, but they're based on physics we understand. If we wanted to send probes to other star systems with current or near-future technology, these are the designs we'd consider. Then there's the truly speculative but mathematically interesting idea of dark visitors. Not every object passing through the solar system gets detected. We find the ones that are bright enough, large enough, or close enough to see, but small, dark objects moving through the outer solar system could slip past unnoticed unless they happen to pass in front of a star or reflect sunlight at just the right angle. How many interstellar objects have we missed? How many are passing through right now that we simply can't see? The answer is probably a lot, and that statistical reality creates space for all kinds of unsettling possibilities. Avi Loeb and others have proposed that we might be surrounded by a galactic communication network we don't recognize. Not radio signals, those we detect, but something more subtle. Gravitational wave modulations, neutrino, beam patterns, quantum entanglement channels, whatever the physics of advanced communication turns out to be. These signals might be washing over Earth constantly, and we'd have no idea because we're not listening in the right way. It's like trying to detect Wi-Fi with a transistor radio. The signals are there, but you need the right receiver to pick them up. Autonomous probe networks make even more sense when you consider the timescales involved in galactic exploration. Light takes years to cross interstellar distances. Even at relativistic speeds, traveling between stars requires decades or centuries. No civilization is going to maintain real-time control over probes operating hundreds of light years away. Instead, you build autonomous systems that can make decisions, adapt to local conditions, and carry out long-term missions without constant supervision. You send them to gravitationally stable regions around stars and gas giants where they can observe for thousands of years, collecting data and transmitting summaries back home whenever a faster probe swings by to act as a courier. Jupiter keeps coming back as the obvious choice for this kind of infrastructure. If you were cataloging stellar systems across the galaxy, looking for ones that might develop technological civilizations, you'd want probes in places that offer good vantage points and long-term stability. Gas giants with strong magnetospheres fit that requirement perfectly. They're easy to find, easy to reach, and they provide natural resources for probe operations. Jupiter isn't special in this framework. It's just one of millions of similar locations scattered throughout the Milky Way, each one potentially hosting its own sentinel network. Some models propose that interstellar probes follow power gradients, seeking out high-energy environments where they can recharge and maintain operations. Stars, obviously, but also magnetospheres, accretion disks, planetary radiation belts. Anywhere electromagnetic fields and charged particles create harvestable energy. If this hypothesis is correct, then Jupiter isn't just a convenient parking spot. It's a refueling station, a place where probes naturally congregate because the physics of energy extraction favors these locations. There's a historical pattern worth noting here. Throughout human history, surveillance and reconnaissance have always involved finding high ground. Mountaintops, satellites, Lagrange points. We put our observation platforms where they can see the most territory with the least effort. If aliens think the same way, if convergent evolution applies to military and intelligence strategy as much as it does to biology, then Jupiter's Hill radius is the cosmic equivalent of the high ground. You can see everything from there, and anything happening on Earth is visible in real time, or at least in the 12 to 40-minute light lag, depending on orbital positions. Imagine a galaxy filled with these networks, millions of sentinel. Systems deployed over billions of years, each one quietly monitoring its assigned star. Some watch systems with primitive life. Others observe worlds undergoing technological development. A few might be tracking civilizations far more advanced than ours. The probes don't interfere. They just record and transmit. And somewhere, far away, something is receiving all that data, building a comprehensive map of galactic development, tracking which systems show promise and which ones collapse before reaching the stars. Maybe the probes activate under certain conditions. Maybe they're designed to remain dormant until a civilization reaches a specific technological threshold, nuclear weapons or radio telescopes or spaceflight, some marker that indicates we're becoming relevant on a galactic scale. 3I/Atlas could be waking up now because we've finally crossed that threshold, or because something we did recently triggered an automated response protocol built into hardware that's been drifting through space since before Earth had continents. These are unverified scenarios, thought experiments, rather than scientific conclusions. But they're not baseless speculation. They're extrapolations from principles we understand, applied to questions we're only beginning to know how to ask. And 3I/Atlas, whatever it turns out to be, has forced those questions into mainstream scientific discourse. Because if these objects are artificial, if we're being cataloged by a network we didn't know existed, then everything changes. Our place in the cosmos, our understanding of intelligence and civilization, our assumptions about being alone or unique, all of it gets rewritten. And we have to confront the possibility that we've never been alone at all. We've just been too primitive to notice the watchers until now. While astronomers debate the nature of 3I/Atlas, a parallel revolution is happening in how we observe the sky, and the timing is either an enormous coincidence or evidence that we're entering a new phase in cosmic awareness. Artificial intelligence has arrived in astronomy, and it's changing everything about how we detect, catalog, and interpret objects moving through our solar system and beyond. The machines are learning to see patterns we can't, finding signals in noise we dismiss, and in the process, they're discovering things that make 3i/Atlas look straightforward by comparison. The revolution started quietly, the way most paradigm shifts do. Astronomers have been using computer algorithms to analyze telescope data for decades. Nothing new there. But recent advances in machine learning have crossed a threshold where AI systems don't just process data faster than humans. They process it differently, applying pattern recognition techniques that can identify subtle correlations invisible to human observers, no matter how carefully they look. An AI trained on millions of stellar observations doesn't just categorize stars by brightness and color. It finds weird outliers, objects that don't fit any existing category, events that happen too quickly or too faintly for traditional surveys to catch. Microflares are a perfect example. These are tiny, brief brightenings in stars or other objects, lasting sometimes less than a second, releasing energy equivalent to a small nuclear bomb, but spread across electromagnetic wavelengths that make them nearly impossible to detect without specialized equipment and analysis. For years, we assumed microflares were rare because we rarely saw them. Turns out we just weren't looking properly. AI-powered telescopes now detect microflares constantly, thousands per night, and nobody's quite sure what they all mean. Some are probably natural stellar activity. Others might be starquakes or magnetic reconnection events, but a few defy easy explanation, showing energy distributions or timing patterns that don't match any known astrophysical process. Microlensing events are even stranger. These occur when a massive object passes between Earth and a distant star, and the object's gravity bends the starlight in a way that briefly magnifies the background star's brightness. Microlensing has been used for years to detect exoplanets and dark matter candidates, but AI systems are finding microlensing events caused by much smaller objects, things too tiny to be planets, moving at velocities that don't fit normal solar system or galactic orbits. Some of these detections last milliseconds. Some show asymmetric brightness curves suggesting non-spherical lensing objects. And a handful exhibit characteristics that researchers describe privately as troubling, though publicly they're just cataloged as anomalies pending further analysis. Transient objects are the real frontier. These are things that appear in telescope images for one frame and then vanish, present for hours or minutes before moving on or fading below detection limits. Before AI, most transients were missed entirely because nobody had time to examine every single image from every single telescope, looking for faint dots that might or might not be real. AI can examine millions of images in the time it takes a human to check one, and it's finding transients everywhere. Most are asteroids or satellites. Some are cosmic rays hitting the detector, but others have proper motion, moving across the sky in ways consistent with real objects at specific distances, and their velocities or trajectories occasionally raise eyebrows. The new survey arrays coming online make this even more intense. The Vera Rubin Observatory in Chile will photograph the entire visible sky every few nights, generating petabytes of data that no human team could possibly analyze manually. The Euclid Space Telescope is mapping the geometry of the universe while simultaneously cataloging everything that moves or changes. The Nancy Grace Roman Space Telescope, set to launch soon, will conduct microlensing surveys, orders of magnitude more sensitive than anything previously attempted. Each of these instruments feeds data into AI systems designed to find anomalies, and they're succeeding beyond anyone's expectations. But here's the uncomfortable part. Some research teams have detected things they're not publishing, not because of conspiracy or cover-up, but because the detections are too anomalous to present without more data. And getting more data is difficult when you're tracking objects that appear briefly and then vanish. Academic careers are ruined by publishing extraordinary claims that can't be replicated. So when an AI flags something genuinely weird, a microflare from an empty patch of sky, or a transient moving at 0.2%, the speed of light, or a lensing event that suggests an object with impossible mass, the researchers sit on it. They wait for confirmation. They run more checks. And meanwhile, the anomaly sits in a database somewhere. Flagged, but not announced. Unexplained, but not forgotten. There are whispers in certain astronomy circles about a class of detections informally called fast movers. Objects tracked by multiple telescopes, showing velocities inconsistent with natural solar system objects, but below escape velocity. Not fast enough to be interstellar, not slow enough to be captured, just weird intermediate speeds that require specific and unusual trajectories. Some people think these are classified satellites or debris from undisclosed military launches. Others aren't so sure, especially when the objects show brightness variations, suggesting tumbling or unusual shapes. Then there's the reflectance curve problem. Most objects in space have predictable albedos. They reflect sunlight in ways consistent with rock or ice or metal. AI systems analyzing light curves from known asteroids sometimes find outliers, objects that reflect light with efficiency curves suggesting highly polished surfaces or geometries that don't occur naturally. These could be measurement errors. They could be strange mineral compositions. Or they could be something we haven't considered, materials or structures that don't fit our assumptions about what space debris should look like. The timing of all this matters. 3. I/Atlas arrives during the same period that our observational capabilities undergo exponential improvement. We're suddenly able to see things we couldn't see before, and what we're seeing is stranger than anyone expected. Maybe that's coincidence. The universe is vast and weird, and better telescopes naturally find more weirdness. But there's another interpretation, one that keeps some astronomers up at night. Maybe we're not discovering new phenomena. Maybe we're finally noticing things that have always been there, objects and events that have been happening around us for years, or centuries, or longer, invisible until we built machines smart enough to spot them. If 3 I/Atlas represents intentional activity, if it's deploying probes around Jupiter while we watch, then the question becomes whether it's alone. Are there other objects we've missed? Are there networks already in place that our old telescopes couldn't detect, but our new AI-enhanced systems are starting to glimpse? Every anomalous detection, every unexplained transient, every microflare that doesn't quite make sense, could be evidence of a presence we're only now learning to recognize. And here's the truly unsettling thought. While 3 I/Atlas approaches Jupiter, while AI systems scan the sky with unprecedented sensitivity, we're reaching a moment where both sides of the cosmic equation are changing simultaneously. They're arriving, or becoming visible, or activating, or whatever verb applies to interstellar probes beginning their missions. And we're learning to see, developing the technology and algorithms necessary to detect things that were previously invisible. Two curves intersecting, one inbound and one outward in capability, meeting at a point in time that feels less like coincidence and more like synchronization. Are we learning to see the universe more clearly just as something out there decides to take a closer look at us? Or have they been here all along, waiting patiently for us to develop eyes sophisticated enough to notice them? The answer might be encoded in the data our AI systems are collecting right now, patterns hidden in millions of observations that we haven't yet learned to interpret. And when we finally decode those patterns, when we understand what the machines are seeing, we might discover that our solar system has never been as empty as we believed. We might find that we're surrounded by architecture we mistook for nature, probes we cataloged as comets, signals we dismissed as noise. And 3 I/Atlas, with its precision trajectory toward Jupiter's Hill radius, might turn out to be not an isolated visitor, but the first one we noticed in a crowd we're only beginning to see.